Assalamu alaikum warahmatullahi wabarakatuh. Welcome to another computer science lecture for 9618A2, and we were doing paper 3. Today we are going to start chapter number 19, computational thinking and problem solving, and 19.1 is algorithms. First of all, we have searching methods. Searching algorithms, as you know very well, are essential in computer science, as whenever you need to check whether a number or a name is found in a specific list or not. For that we use searching methods. In A level we have two types of searching algorithm. One is known as a linear search that you already know, and another one is known as binary search. Now, linear search, as you know very well, works in a systematic way. It compares every element in an array with whatever search term you have inputted, and if they are same, it outputs the message is found, stops the loop, and if it does not found whatever it was looking for, then it outputs an error message. Efficiency. It is less efficient on larger lists as it may require checking each element. It is best suited for small arrays or when elements are unsorted. Now, implementation of linear search. First, you always start by comparing the first element with your search term, and then if there is no match, you move on to the next element. If there's a match, you stop. The time complexity is written as O(n), where n is the number of elements in the list. So if there are 50 elements, you'll write the complexity as O50. Big O notations are used to describe the performance or complexity of an algorithm. You'll get to learn about them later on. Okay, this is a simplified version of a linear search algorithm. You already know it from your O levels, from your AS level, so I'm not going to explain it again. You can just read through it, and let's move on. Now, something which is unique in A2 paper number 3 is binary search. It is a very efficient searching algorithm, far more efficient than a linear search. It compares the target value to the middle element of the array and repeatedly halves the search interval. The lists have to be sorted prior to applying binary search, otherwise it cannot work. This thing cannot work on an unsorted list. It's significantly more efficient than linear search as it can find its required target in less number of steps or less number of comparisons. So if you have this array, then it would find the middle point, and then it would compare the middle point with your required term. Let's suppose if you're looking for a 1, then it would half it again, and this time 1 is equals to 1, it will stop. Now how do you implement a binary search? Identify the middle of the list. That's the first thing to do. If the middle item matches the target, return its index. If the target is less than the middle item, narrow the search to left half. If it is more than the middle term, like let's suppose you're looking for a 3 and the middle term is 2, so that means you'll move on to the right hand side. Repeat the process until the target is found or the search interval is empty. The time complexity is O log 50 or O log n, with n be this is supposed to be O log n, not O log 50, where n is the number of elements. So for example, if you have 50 elements in an array, then for this it will be O log n. For linear search, the complexity will be O(n) or O50, whereas for this one it will be log 50, that is 1.69. So it's far less than your linear search. This is how a binary search works. You can look at this algorithm. For example, you're trying to find 9. Now you compared the first element with the half of it, doesn't work. Then 7 is smaller than your search element 9, so we move on to the right half. Then the half of 7 and 13 would be something like 11. Then you move on to the left hand side, and finally between 7 and 11 you'll find your search term, that is 9. Now here's an algorithm for binary search. Let's suppose we are trying to find an item that is in a populated 1D array my list, and it goes from 1 to 50. Now these are the variables that you'll need to declare. You need to declare upper bound, lower bound, count, and item as integer. Why am I declaring item as integer? Because this is a list of numbers, assuming otherwise I would have made item or search term as a string. Now remember, like I said, paper 3 contains both algorithms and theory part. Up till chapter number 18 we only had theory. Now in chapter number 19 and 20 we are going to have algorithms as well that you'll need to learn. Then we'll declare found as boolean. In the upper and lower bound we'll have to put the minimum range for our array. Now first of all we are going to ask the user to enter item number to be found. Then we input it, then found will be false, then we are going to repeat. Now remember, we have to calculate the half of our array. So how we do that? Count will be equal to int upper plus lower bound divided by 2. Now why are we applying the int function? In order to convert this into a whole number. So if item equals to my list count, then found equals to true. And if item is greater than my list count, then lower bound equals to count plus 1. Otherwise, if it is less than my list count, then upper bound would be count minus 1. So you can shift to right hand half of the array or the left hand of the array until found is true or lower bound equals to upper bound. If found equals to true, then output item found at position count. Otherwise, item not found. Simply. Linear versus binary search. Linear search is useful in unsorted or small data sets, where binary search is optimal for large data sets, for sorted data sets. Linear search has a worst case complexity of O(n), whereas binary search has a worst case complexity of O log n. Linear search is simpler, whereas binary search is a bit complex. Linear search only functions correctly on binary search only functions on sorted list, whereas linear search has no such requirements. Efficiency of binary search increases with the size of data, whereas complexity of linear search increases with size of data set. Now if it is not written in the question, then you are free to apply binary search or linear search, whichever you find easier. But if it's written in the question that okay, apply a binary search and you apply a linear search over there, you lose all of your marks. No matter what, 4, 5, 6 or 7 marks, whatever are the marks for the question, you'll absolutely lose all of them. Next we have the sorting methods. Now what are the sorting methods? So far you have only encountered one sorting algorithm, that is the bubble sort. It was there in paper 2 of AS, it was there in paper 2 of O levels. Now in A levels, in A2 basically we are going to study two methods of sorting, bubble sort and insertion sort. So about bubble sort you already know that it is inefficient for larger data sets. And how it works, it repeatedly swaps, it repeatedly compares every value with its adjacent value and swaps them if it is in the wrong order, and it keeps on doing that unless and until no more swapping is required. The complexity of algorithm, that's something new. The best case scenario has the complexity of O(n), n is the number of elements. Worst case is O(n) square, and average case is usually O(n) square as well. Now it is easier to simple, it requires less memory, and it can be practical if data is almost sorted. Disadvantages: it is quite inefficient, it has higher complexity, and it can be outperformed by merge sort, not a part of our syllabus, or even insertion sort. Here's the algorithm. You already know it very well, so I'm not going to explain it. You have been studying it since O levels, so just go through it and we can move on. Next we have something new, that is insertion sort. It is a straightforward but very efficient sorting algorithm which is suited for small datasets or nearly sorted arrays. Insertion sort simulates the way one might sort playing cards in their hand. The array is virtually split into a sorted and unsorted part. Values from unsorted part are picked and placed in the correct position in the sorted part. So how it works: this is the first element, it will mark it as sorted and it will turn like this. Then it will compare it with the next element and it will decide that okay, one should be placed before 23. So it will do that. Now this is the sorted list, this is the unsorted list or sorted part and unsorted part. Next, it is going to take the third element and compare it with the first two elements, and it will decide, okay, 10 should appear between 1 and 23, so it will insert it over there and move 23, 10, 5 and 2 ahead, so it will become 1, 10, 23. These three will be sorted, 5 and 2 are unsorted. Then it will do the same with 5 and finally 2, and we'll have our sorted array. Algorithmic process. This is basically what I just explained you. Best case complexity is O(n). Worst case and average are also O(n) squared. In this regard, it is just like your bubble sort. Advantages: it is simple and intuitive. It is efficient for a small data set. It maintains the relative order of equal elements. It requires minimal additional memory. Disadvantages: it's not very good for large data sets. Time complexity increases quadratically with the number of elements. This is the algorithm that you need to learn. So we are going to have an upper bound, we are going to have a lower bound, we are going to have a count, a temp, a place and a key. All of them will be integer if we are considering an integer array. Otherwise, temp would be, as you know, it would be string and so on. So first of all, we'll assign values to upper and lower bound according to our array. Now we are going to run a for loop for this. For count lower bound plus 1 to upper bound. Key would be the value in my list count, and place will be count minus 1. So if you are working on a string array, then key and temp will need to be string data type variables. If my list place or if my list count minus 1 is greater than key, then you run a while loop. That while place is greater than or equal to lower bound and my list place is greater than key, then what you do, you take the value at my list place plus 1 and you put it in temp. Then at my list place plus 1, like the next value, you'll put the value of my list place. Then you'll take the value from temp and put it at my list place. And finally, you'll decrease the value of place by 1 and while. Finally, you'll take the value stored in key and you'll put it at my list place plus 1 and if next count. That's it. This entire array, you'll kind of need to learn it, and by learning it, what you'll do, you would be able to solve it efficiently in an exam. Next, we have some abstract data types. These are the theoretical constructs that define data types by their behavior. They can now ADTs basically encapsulate both data items and their operations. You studied about them in chapter number 13 as well as chapter number 10 as well. Over here, we are only going to look at the algorithms needed to perform different operations on abstract data types. We are not going to go in detail of what it is and how you can declare it. That part is taken care of in chapter number 13. In a stack, we have algorithm for push operation or inserting a value. First of all, you check if it is already full or not. If top of stack is less than stack pointer, then you'll add +1 to top of stack and you'll add item at top of stack. Otherwise, you'll output stack is full, cannot push. For pop operation, first of all, you'll decrease top of stack. If top of stack is equal to stack pointer -1, then you'll say, sorry, stack is empty, cannot pop, because that would mean top of stack would be -1. Else, item would be whatever is at the top of stack, you'll put it in item and then you'll decrease top of stack with -1. Normally, you don't have to write the whole algorithms for these operations. This will be given to you something like this. There will be some blanks given to you and you'll just have to fill it up, but obviously even for that, like something like this, but even for that you'll need to learn these entire algorithms so you can correctly fill in the values. For a queue, for an NQ operation, this is the pseudocode. If number in queue is less than size of queue, then if end of queue is less than size of queue, then end of queue would be end of queue +1. Otherwise, end of queue would be 0 because queues are circular. And if number in queue would be number in queue +1 because you're adding a new element. And then queue end of queue would become item. Otherwise, if this condition is not met, then you'll simply say sorry, queue is full, cannot in. For dequeuing or deleting a value, this is the algorithm. If number in queue is 0, then you output sorry, it is empty, you cannot dequeue. Otherwise, you'll take element at front of queue, the position front of queue, you'll put it in item, then front of queue. If after dequeuing front of queue becomes size of queue, then you make it 0. Otherwise, you do front of queue equals to front of queue plus 1, and size of queue becomes size of queue minus 1, and that's it. For linked list, if you have to insert something in a linked list, then you are going to need an add item, you're going to need a start pointer, a heap start pointer or a free list pointer, and a temporary pointer. Then you are going to need a constant null pointer equals to -1. You are going to need a procedure for this. Procedure insertion item add. If heap start pointer equals to null pointer, then output linked list is full. Otherwise, start pointer will go in temp pointer, heap start pointer will go in start pointer, and then finally my linked list pointer. This is the pointer array at the position of heap start pointer will go into heap start pointer. My linked list start pointer add item will be stored at this position, and temp pointer will be stored in this position, because you'll have to adjust the start pointer for the linked list pointers. And if and proceed. For deleting a value from a linked list, you are going to need item delete, old count, count, start pointer, heap start pointer, and temporary pointer. Null will be -1, constant. For a deletion operation, if a start pointer equals to null pointer, then you'll say sorry, linked list is empty, you cannot dequeue. Otherwise, start pointer will be stored in count, and while item delete is unequal to my linked list count and count is not equal to null pointer, what you are going to do, you are going to place count into old count, and then my linked list pointer count will be stored in count, and that's it. If count equals to null pointer, then output item delete not found. Otherwise, my linked list pointer count will be stored in temp pointer, heap start pointer will be stored in my linked list pointer count, count will be stored in heap start pointer because you don't need that element anymore, temp pointer will be stored in my linked list pointer, and if. That's it. Algorithm for search operation. If you have to search a value in a linked list, for that you are going to need item search, item pointer, whereas null pointer will remain a constant, and you'll need to make a function for that. Function search returns integer because we are assuming it is a linked list of numbers. Declare found as boolean. Item pointer will become start pointer and found will be false initially, while item pointer is not equal to -1 or the null pointer and found is false. Then what you do, item search. If my linked list item pointer is equal to item search, then found will be true. Otherwise, item pointer will become my linked list pointer item pointer at the position of item point, and it will keep on moving. And if and while return item pointer and function. This will basically be the value of the search operation. Alright, next we have binary trees. A binary tree is a tree data structure where each node has at most 2 children, not more than 2. It is referred to as the left child and the right child. Left child node have lesser values and right have higher values always. They as compared to their parent node. There are many uses for a binary tree, for example, used in syntax analysis, compression algorithms, database indexing, and 3D video games. This is what a binary tree looks like. Now, how you can create a binary tree? You'll declare type node, you'll declare an item as integer, left pointer will be integer, right pointer will also be integer. Then you'll declare an array of 8 elements, 1 2 3 4 5 6 7. This should be 0 to 7, sorry, my mistake, of node that you just created. declare a root pointer as integer and declare next free pointer as integer. This is how you create a binary. Hopefully you will not be asked to create a binary tree. Okay, the root pointer points to the first node in a binary tree, and a null pointer is a value stored in the left or right pointer in a binary tree to indicate there are no nodes below this node on the left or on the right. Now if you have to insert an operation, now this thing I have kind of just added as a precaution, but anyways, you are going to need a root pointer, a next free pointer, and an item pointer, an item add, and an item add pointer. Then null pointer would be -1, and this is the procedure you're going to need in order to add something into a binary tree. You can just read it. This typically will not be there in your paper, but just in case, since a binary tree was mentioned in the syllabus, I've added the algorithm just in case. And then it goes on. For a search operation, this would be an algorithm. Again, you are not really going to need it. This is just as a precaution, so I'll just advise you to read it once and then be on your way. That's it. This type of question has never been in the exam, and I don't think so they are going to give such a complex algorithm in your paper 3 anytime soon. Anyways, then we have graphs can be represented as abstract data types as well. Okay, so they are a collection of nodes, and the fundamental components and variations of graphs include the nodes that represent the entities, the edges represent the relationships between these entities. Over here we have 3 nodes and we have 3 edges as well. In a directed graph, edges have a direction implying a one-way relationship. Conversely, in undirected graphs, there are straight lines, no arrows, so you can have mutual relationships as well. Weighted graphs assign a value to their edges, whereas unweighted graphs don't have that. Cyclic graphs contain at least one sequence of vertices that form a loop, just like this. Acyclic graphs do not contain loops, they just carry on. Graphs are defined by their features. Adjacency, this denotes whether two nodes are directly connected by an edge or not. Path refers to the edges connecting a series of vertices. Degree of a vertex, the number of edges incident to a vertex. In directed graphs, this is classified to in degree number of incoming edges and out degree number of outgoing edges. For this one, like this node has a degree of 2 because it has 2 edges connected to it. Graphs provide an efficient way to model and solve complex problems that we kind of discussed in our last lecture as well, chapter number 18. Then we have the dictionary data type, abstract data type. It consists of pair of keys and values. Basically, we looked at dictionary data type in chapter number 13 as well. So let me just show you a diagram to better make you understand. This is what a dictionary data type look like. Every key is assigned some values. Keys in the dictionary are unordered, and by using corresponding key you can retrieve a value from the dictionary. The dictionary differs from a set because the values can be duplicated, whereas in sets we cannot have them duplicated. As dictionary is not an ordered list, it can be declared using a linked list as a part of definition. Okay, again, this is just as a precaution. You can have a look at it, but you don't really need to try and learn it. It won't really be there in your exam. Implementation of ADTs, arrays and linked lists. Stacks operating on a last in first out basis are very important ADTs. You can implement them using arrays like you studied in your chapter number 10 as well, that first of all you create an array with predefined maximum size, then you perform a push operation to insert values or a pop operation to remove values. You can use a top or peek function in order to view the top element without removing it as well. Advantages: it is very simple and has a constant time limit for push and pop. The complexity is 1. Limitation: fixed size of array can lead to space inefficiency. You can also use a linked list to implement a stack. It comprises of nodes, each containing data and a reference to the next node. Then push operation would mean when you add a new node at the beginning of that would mean you would add a new node at the beginning of the list, and pop operation would remove the node from the beginning, maintaining stack's LIFO nature. Advantages: you can use linked list for dynamic resizing. Unlike arrays, once they are created, you cannot resize them, but in linked list you can do that. Limitations: you are going to need additional memory for storing node pointers, because in linked list pointers cannot be saved together. For queues, you can also use arrays or linked list. How you can implement queues with arrays, you have already studied in chapter number 10. You might review it a little bit. Then you can use the enqueue operation to add an element, or dequeue operation to remove an element. Limitation is the fixed size and complexity of handling circular indices. If you use a linked list, then structure is very much similar, but enqueue happens at the end and the dequeue happens at the head. That's the difference. Advantages: efficient memory utilization, because linked list is always dynamic. For dictionaries, you can implement them using hash tables. These convert keys into array indices, so you can use them in order to retrieve values stored at that position. Techniques like chaining, linking entries with same hash, and opening address can be used to maintain efficient operations. Hash tables can be resized as well. Implementation of ADTs using other ADTs. You can implement stacks using queues by doing a careful manipulation of enqueue and dequeue methods to maintain a LIFO property, and then you can also implement queues using stacks. Algorithm efficiency and comparison. Definition of algorithm efficiency: it refers to how effectively an algorithm performs, especially in terms of speed and resource utilization. The criteria for comparing algorithm: we compare it on basis of execution time, like which algorithm takes how much time to run, as well as measuring execution time, how much time does it take to execute it, and factors include processor speed, algorithmic complexity, and the size and nature of input data. Memory usage and the amount of memory space an algorithm needs during its operation. Now there can be two types of memory usage. Static memory means fixed amount of memory, like in arrays you cannot change or resize them. Dynamic memory means you can change the size of your list during runtime. Now big O notation. Yeah, I've deliberately left this line. You can read it yourself. It's not really important. Big O notation. It is a mathematical notation that describes the limiting behavior of a function when the argument tends towards a particular value or infinity. Basically, it is used in computer science to classify the complexity of algorithms. It is used to describe the execution time or a space requirement, means complexity of an algorithm, in terms of the size of input data n. Time complexity with big O notation. Constant time would mean O1. The execution time of algorithm remains unchanged no matter what the size of input data is. Linear time On. Execution time increases linearly with the size of input data, or kind of like a direct proportional relationship. Quadratic time On squared. The execution time increases quadratically, like 4 times with the increase in input size. This would involve nested iterations, etc. Logarithmic time would mean O log n. The execution time increases logarithmically with the increase in input size, a characteristic of algorithms that divide the problem into smaller parts, such as in binary search. Space complexity with big O notation. You can either have constant space like O1, no matter the size of your input, your computational complexity, your processing power will remain same, or linear space. The more input you use, the more memory, the more resources it will require. Hence, it's written as On. Factors influencing algorithmic efficiency. We have the size of input data. Generally, the larger the data set, the more complexity it will have. data structure selection, the choice of your structure, like whether you're going for an array, for a linked list, for a tree. It also has a direct relationship with how complex your algorithm will be. Algorithm design strategy. Certain design strategies like divide and conquer, dynamic programming, and greedy algorithms can greatly influence efficiency. Last but not the least, how to evaluate algorithmic efficiency. We have a comparative analysis and we have a theoretical analysis. For comparative analysis, you can do a direct comparison. You can run two algorithms with the same input and you can compare their performance in terms of execution time and use of memory. Then we have a process known as benchmarking, where we use standardized tests or standardized data sets to evaluate the performance of an algorithm. Theoretical analysis includes predictive modeling, where we utilize big O notations in order to predict how complex an algorithm will be. Worst case, average case, and best case scenarios, analyzing how the algorithm performs in different scenarios in order to get a comprehensive understanding of its efficiency. And that's absolutely everything, plus a little bit of, in fact, a lot of things that are a little bit out of the box, but since the syllabus is quite ambiguous for chapter number 19, to be honest, hence I've included a lot of things which which you probably won't ever find in your exams, but I had to cover every aspect of the syllabus so that you can tackle a surprise question if the examiner is in a bad mood someday. Anyways, that's everything, absolutely everything, plus a lot of some things that you would do fine without as well, that you need to know for chapter number 19.1. And hope you like this lecture. Give me a thumbs up and share it with your friends. Leave your comments below. I'll see you guys in the next class. Till then, take care. Allah Hafiz.